Welcome to Chemistry 111. We'll start with just some news at the top of the. I reiterate some of this at the end again, but big thing first off is just a quick reminder on lab. That lab is split up into two separate parts. One is the 7 regular labs that you have to attend at least 6 of. I dropped the lowest one. And 2 is the online lab. There are 4 or 5 online labs, but you only have to do 3. There is a approximate due date that's listed on the syllabus, but it's only an approximate due date, trying to keep you busy throughout the semester so that come the end of the semester and suddenly you're stuck having to do them all at once. Some of them might take a couple days. Like, for example, one of the ones I'm making my Chemistry 112 class do is a vitamin C lab. They cut some apple slices, some banana slices. They leave them out like over a night or over a day and like sprinkle some vitamin C tablet powder on one set of them and then leave the other one as a control group. Obviously, they don't have to take the video the whole time, but they take a video of it setting up, take a video of them looking at it at the end and answering a question about it. So, but I mean, that's one where if it's the end of the year and you've left that to the very end, not only is that going to take too many days to worry about, but I don't want to have to be grading them all at the end. So be working on that. But that's not like, if you're late on that, that's not the end of the world. 2, I've given you all your tests. Your tests should be in your email. Theirs are due next Wednesday. Make sure to turn them in. Make sure to write up things, explain your reasoning, show your work in it. There's not a ton of math problems, but the math problems there are, show the work. Because if you're wrong for whatever reason, if I see what you did wrong in your work, you only lose like maybe 2 out of 5 points, 1 out of 5 points, 3 out of 5 points. Maybe you can still get most of the credit. If I see what you did wrong and then it's a 2-part problem where you have to use it on the next step, well, I can definitely give you credit there. Because like, oh, she screwed up on part 1. Part 2 is screwed up because part 1 was screwed up. Full credit for part 2. But no work, I'm just like, well, they're both wrong. So just keep that in mind. That's due next Wednesday. You have a week since I sent those out. Okay. So let's continue with chapter 4. Now, as we're just talking about that energy, light can be produced as an energy. That light produced by typically white lights, like fluorescent light bulbs, is actually a full spectrum of light. That you have a Roy G. Biv, the whole color of the spectrum that we don't see because when it all goes together, it appears to be white. But if you hold a prism up to that light, you can split it into the individual wavelengths. And that certain elements, when you burn them, will also produce various lights. And that's the same concept we use in fireworks. Well, there's another way to get colors from elements, and that to electrically excite glass tubes filled with various gases. So remember our cathode ray tubes, where we put the electrical source through them and they glowed where the electrons hit. Well, those tubes were mostly vacuum tubes. They were empty. They essentially had nothing to block the gas. No gas to block the electrons. Well, if we have a tube filled only with certain types of gas, what we see is the tube starts to glow when electricity is run through it, such that those orange lights that used to be all present everywhere were neon gas. Thus, we have the neon lights. Sodium gas, vaporized sodium. Most of the street lamps we see around town that work in light, that kind of have that like kind of pale yellow glow, that's produced by the electrically exciting sodium vapor. But we could also get a similar effect from helium. Hydrogen, if you electrically excite hydrogen, it's going to be red. Carbon dioxide would be white. And mercury vapor would be a blue excitation. Now, if we were to take those same colored lights and run a prism through them, instead of getting the whole spectrum that we would see otherwise, we get several distinct wavelengths that get diffracted off. This is called an emission spectrum, also called a line spectrum. Emission spectrum because it's the light emitted off of the gas, and a line spectrum because it's split into individual lines. I think we'll look at this on lab 3, if I'm not mistaken. But in lab 3, we'll look at the properties of light, and we'll actually observe some like neon tubes and hold up prismatic glasses and actually observe these line spectrums. So you see hydrogen, which was red, is made up of one wavelength of like dark blue, one of like kind of a lighter blue, maybe one green, and one red. Mercury, which is a more complicated element, it's in the deep transition metal. You see like a couple blues, couple greens, couple yellows, a couple oranges, and a red. And neon, which is a noble gas, you see a whole lot of lines. All those colors come together that produces our orange coloring, or our like blue coloring, or our red coloring. So remember on the color wheel that are like the opposite colors, the absence of that color is often responsible for the coloring. So in hydrogen that's red, see not a whole lot of green absorption. In mercury, which is blue, would be not a whole lot of yellow. We see neon, which ends up being orange. We don't see very much blue. See a lot of oranges and greens, but not much blue in the wavelength. Okay. Now, this is partially brought about by a photoelectric effect. That we started by talking about light as a wave, that we could describe it as a wave with an amplitude, a wave with a certain wavelength, a wave with a certain frequency, and all that works. But sometimes light can act as a particle as well, like a discrete energy packet. Now, when you shine a monochromatic laser upon a metal, so monochromatic means a single wavelength laser on a metal. Depending on the laser and depending on the metal, when you shine the light on the metal will produce electrons. There'll be like electrons will start popping off and can be detected by some current sensor. As I said, this will depend on both the metal and the frequency of the frequency of light. Such as if I use red on aluminum, maybe nothing happens. But if I up it to a, say, green laser, suddenly electrons start shooting off. If I use, instead of aluminum, maybe I use iron. Maybe I only need a red laser to make electrons shoot off. And so it depends. Now, increasing the intensity of the laser only increases the amount of electrons. So if I have a green laser pointer that works on aluminum, and I make it a high-powered green laser pointer, I don't get, it doesn't work better. It just shoots more electrons off. So that red laser pointer, if I shot it at the aluminum, it doesn't work. Even a high-powered red laser still won't work, because you're just shooting more particles of light. More particles of light just mean if it works more. If it doesn't work, it's still more doesn't help it. So Albert Einstein explained this as the photoelectric effect. This is where he originally got his Nobel Prize from. The photoelectric effect that states that as light is acting as tiny packets of energy, called a photon. So a photon is a tiny packet of energy of light that as it strikes the metal, it transfers this energy. And this will cause electrons to be ejected. So the light hits there, transfers energy. That energy is used to kick out an electron. Just like when you stand out in the sunlight and you let the sunlight hit your skin, you'll start to feel warmer. Why is that? Because that sunlight contains energy in there. As that energy hits your skin and is absorbed by your skin, that raises your body temperature, raises the temperature on your skin because of the energy from that light. Now, these energy of light packets could be described by this equation. The energy is equal to h, which is a constant, times frequency. H, as I said, is called Planck's constant, or maybe Planck, but it's 6.626 times 10 to the negative 34th joule seconds. Don't worry about memorizing this constant. You will be given it on any test you need. You can always look it up. It's a obtruse number. But what that does is it turns units of inverse seconds, which is the unit of frequency, inverse seconds into joules. Joules is the main measurement of energy of a system. We can use joule to describe how much energy it takes to heat up water by 1 degree C, 1 gram of water by 1 degree C. I mean, that's a calorie technically, but joules and calories are related. So joule is a main measurement of energy. So Planck's constant converts a frequency, which is inverse seconds, to joules. Now, each metal will have a minimum energy required to eject a photoelectron. We can describe it with a work function, phi. The long story short is that if the light has enough energy, the electron will be ejected. Any excess energy gets converted into kinetic energy. So if I shine a green laser pointer and the energy of the green laser pointer is greater than phi, the electrons are shot out with a velocity equal to the kinetic energy, related to the kinetic energy. If I shoot a blue laser pointer at the same thing, a blue laser pointer would have more energy, and so the electrons would be shooting off faster. If I shot a red laser pointer, it has less energy, and if it isn't greater than phi, then the kinetic energy is essentially zero. The electrons do not leave. So we're going to do some practice of using these three functions. The first two are going to be used way more than the last two. So 580 nanometers, and we're going to go to frequency. Then we want to go to frequency to energy. And finally, what is the kinetic energy if phi is 1.52 times 10 to the negative 19th? Okay. Here's where I go to the friendly neighborhood .cam. This is where we really need to make sure we understand our units and unit conversions, because nanometers, you're going to be given nanometers, and we have to have this in meters because C equals lambda nu. We're solving for nu, our frequency. C is equal to 2.998 times 10 to the 8th meters over seconds. In order meters to cancel out to give us seconds, well, inverse seconds, we need 580 nanometers in meters. So 580 nanometers, there is 10 to the 9th nanometers in 1 meter. 1,000 meter, 1,000, there's 1,000 millimeters in a meter. There's 1,000,000 micrometers in a meter. There's 1,000,000,000 nanometers in a meter. So milli, micro, nano. So that means this number is actually 5.80 times 10 to the negative 7th meters. You got to get used to doing that. If you don't, it will hurt you. Now, to solve for my frequency. So I'm going to divide both sides by lambda to give us our frequency. So I've rearranged the equation. 2.998 E8 divided by 5.80 E negative 7. You got to make sure you do order of operations. You got to make sure you put this in right. This is one of those things that will get you if you're not careful. It will get you because you're dividing by a scientific notation, which means there is so many places where you could screw this up easily. Times 10 root 8 divided by 5.8 divided by 10 root 7. So I'm doing that right there. I left my nice calculator in the office. I'm going to worry about solve that. So I get a really big number, and that is okay. 5 point, I'm going to say 17 times, let's see, moving the decimal, 3, 6, 9, 12, 14. 5.17 times 10 to the 14th inverse seconds. That's okay if that's a big number. That is a reasonable number for frequency. As we'll see, the energy is actually very small, all things included, because E equals H nu. So the second part, we asked to solve for the energy. Well, we have our frequency right there. H is Planck's constant, so 6.626 times 10 to the negative 34th joule seconds times 5.17 times 10 to the 14th inverse seconds. So the seconds and seconds cancel out. So right now, I take my number. So I got to clear that out. 6.626 times 10 root negative 34. Yeah, that's a massive one. Times 5.17 times 10. 10 root 14. So, all said and done, my result of that, my energy is 3.4, we'll say, 3.43 times 10 to the negative 19th joules. So that big frequency is actually converted into a rather small energy. Rather small energy. But that is okay, because you're talking about the energy in one photon of light. It's like one little molecule of sunlight hitting your skin. If it was any greater than this, you would quickly overheat. If we went out into open sunlight, we would like burst into flames. It's because we're getting hit with millions and trillions of particles of light every second. So this little amount of energy makes it within reason. The last part, what is the kinetic energy if this is our energy and our work function phi? So we're literally setting up 3.43 times 10 to the negative 19th minus 1.52 times 10 to the negative 19th. That's joules. That's joules. Where did I get the 1.52? Remember, I told you that at the very beginning. You can't really see it because of the chords, but it's right up there. So I just subtract those two numbers. So don't think that, oh my God, this phi thing is making it that much. It's not. It's not. It's just addition, subtraction. So puts it 1.91 times 10 to the negative 19th joules. So does light get ejected? Yes. And it has that much energy. We could actually calculate what is the velocity of here, because kinetic energy is what? Also equal to 1/2 mv squared. Now, that may not look like a very big number, but got to remember, what is the weight of a electron in kilograms? It's going to be a very, very small number. So all said and done, I think, if I remember right, I may have calculated in the past, the velocity of an electron is pretty darn fast, all said and done. So, just quick, here's all the work. Don't make it harder than it has to be, but keep in mind, you can always go back and look at this later. If you're like, oh, I missed his work, or what did he do, or how did he do it? You can always go back and look at this later. So here's where we get to, we're moving away from light, and we're looking at actual elements. We're going to relate this back to atoms and elements and electrons and all that stuff, because this whole chapter is actually about understanding the electron cloud. When Rutherford did the gold foil experiment, when they did the gold foil experiment, and we found a small nucleus in the electron cloud, we didn't go much further than that. We found that we found that, we have a nucleus. It's big positive charge in there. We have electrons somewhere in the cloud, but we didn't really explain how they stay in the cloud or much about what that cloud actually looks like. So it's not till we have a Danish physicist by the name of Niels Bohr who eventually goes on to try to propose a model to fully explain this. And this is based on what we know about light, what we know about the photoelectric effect and all the atoms. So Bohr's model proposes that electrons are orbiting the nucleus at a specific distance. So as a specific orbit, like just how the Earth orbits the sun and the moon orbits the Earth. They have essentially a set distance with discrete energy levels. The lowest energy level is also the closest to the nucleus, and that would be called the ground state. And from there, any further energy levels that are not populated are called excited states. So imagine like we have a solar system like we have right now, but instead of planets orbiting at all the spots, we have orbiting locations. So if you could start from Mercury, and then if Mercury were to get a bunch more energy, like say you put rocket boosters on Mercury, you could boost it up to where Venus is. It's going to take some energy to move it away from the sun, but you could move it up to where Venus is. You give it a little bit more energy, you could move it up to where Earth is. But given enough time and you allow the energy to leave, it would go back to its original orbit. That's the same way on our elements, our electrons. They're going to have a set orbit at a set distance. And each orbit can only hold so many electrons moving around. But if you give it energy, it can move to a different orbit that is further away. And depending on these differences, light will be absorbed or emitted as it moves from location. As it absorbs light, it will jump from one orbit to the other. However, it needs a specific amount of energy to get there. So if Mercury tries to go to the Venus orbit and it doesn't have enough energy, it doesn't go there. It falls back down. It doesn't get to a different orbit. It doesn't stop. There's only set locations. If like you're walking up a staircase and you don't pick your foot up high enough, it's a steep staircase. You don't pick your foot up high enough and step onto the stair. You don't suddenly make your way up to the next stair. You fall. You trip. If you don't lift your foot high enough to get to that next step, you're not going to make it. You just fall back down to where you're at. So the same thing with these orbits. There are set orbits. If you do not absorb enough energy to make it onto that next orbit, it doesn't get absorbed. That's that red photon doesn't work on certain metals because it doesn't have enough energy. It doesn't make it. Now, when light is absorbed and the electrons get excited, they go to a higher energy state. When they are allowed to calm down, the excitation stops, they emit that energy back out as light. So when we saw the neon lights, the sodium lights, what's happening? You're electrically putting energy into these elements. They are exciting the electrons up, and they're allowed to relax and be excited again and again as they absorb the electricity, turn it into light energy. Absorb the electricity, turn it into light energy. So all this emission spectra that we see is all due to this excitation relaxation process that all elements have. Now, this is a nifty little equation that we will never, ever, ever use. It's called the Rydeberg Equation. It's basically that the energies could be modeled for a single electron in a hydrogen atom. So remember that emission spectra at the beginning of this beginning of lecture today, that there's 3 wavelengths of light we saw for hydrogen atom. We saw that red, we saw like maybe one of that green, we saw one of those like blue. Well, this equation right here was able to predict where they would come out. They could take a ruler and measure those distances and get it spot on based on this equation. Basically, they modeled the energy of those energy levels for an electron. Now, reading the equation, it says 1 over the wavelength, which is 1 over the distance, is equal to a constant for hydrogen times 1 over n squared of the first possibility minus 1 over n squared for the second possibility, where n are integer values. So it's saying the 1 over the wavelength is equal to a constant times 1 over ground state squared minus 1 over the second energy level squared. So 1 over 1 minus 1 over 4th times a constant predicted where this first energy level would be. And then we could see if we 1 over 1 minus 1 over 9, which is 1 over 3 squared, would give another energy level. And you could also imagine one for 1 over 2 squared. So 1/4 minus 1/9 as another possibility, and so on. So you could predict all the energy excitations for a hydrogen atom using this. The reason I say we're never going to use this is because it only can predict for a hydrogen atom, because hydrogen atom has only one electron. That makes it very, very simple to predict for. Once we add a second electron, the math becomes infinitely more complex, and it's no longer possible to easily model this, and so we stop bothering. It's going into some quantum mechanics stuff that we're not going to worry about. So I'm not really going to show this one in action. We're not going to really worry about it so much because I'm not going to ask you any homework about it. I'm not going to ask you any homework about it, and I'm not going to put it on the test. So going back to light for a brief second. Remember, light was able to act as both a wave and a particle. So with this in mind, scientists began to start thinking, well, we know light can act as a wave, mostly a wave, but often a particle. Well, matter is mostly a particle. Could it possibly act like a wave? So we have some really smart French physicists like Louis de Broglie who proposed that matter should be able to act as a wave nature. However, due to its macroscopic scale, we cannot really observe this. If you go down to the nanoscale, yes, all matter acts as waves as well. And we can truly see this when we look at electrons or try to predict electrons. Electrons have a wavelength based on their momentum. Momentum is mass times velocity. So they have a wave-like nature in their momentum. We get a bunch of famous names coming up like Heisenberg. Werner Heisenberg presents his uncertainty principle that essentially that because of this wave-like nature and among other things, you cannot accurately know both electrons' position, which is a particle quality, and its momentum, which is the wave quality, simultaneously. It's basically that there is an uncertainty, an unknowingness. The uncertainty is how accurately you know this. Uncertainty to both of these things. And the uncertainty can never be greater, the certainty can never be greater than this number, a certain number. It's like something like 4 pi something. And basically, the more certain you know one, the less certain you know the other. So you could take a snapshot and know exactly where an electron is, but the momentum could be any number. If you got a good idea of where the momentum is, the exact momentum of electron, the uncertainty says that electron could be anywhere from in this atom to over in another atom. It's like the uncertainty blows the size limitations of this atom way out of the water. So we cannot know both really well simultaneously. So we have people like Erwin Schrödinger develops a mathematical wave equation that we will not worry about. We are not doing quantum mechanics. We're doing the barest skimming of the surface, the barest tangent of a line touching quantum mechanics. But proposed a wave equation that essentially describes the electron's orbit as a series of orbitals. These orbitals are a 3D region of distinct energy level where the electron is most probable to be found. So it all comes down to probability, really. It's saying that left picture is the mathematical probability of where you're going to find the electron. Each of those little dots suggests a probable location. And the more intense the dots, the more probable where it's at. But all said and done, if you expand that and just kind of finish up the dots, you get like a sphere of where this electron is at, saying that we don't know for sure where the electron is in this orbit, but it's somewhere in this region. Just like we don't know right now, I don't know exactly where the QB is during the Super Bowl, but I have a good idea he's probably within the stadium somewhere. Otherwise, he's not going to be a very good QB. So we have a probable idea of where this electron is, and that takes care of we can't know this certain, but we know approximately where it is. Now, these orbitals, these energy levels of similar size and energy are in the same principal energy level shell. So we can break this down into various shells that as we increase the shell, we are going to increase the size and the distance from the nucleus. It is a Russian nesting doll of orbitals that each shell, like so, I'm going to go to the doc cam for a minute so I can draw this out. So essentially we have the little nucleus, plus we have one orbital shell. We have one energy level. This is maybe our ground state. Then we could have another sphere, bigger, further away, with the boundary around there that's surrounding the first one. So this is energy level 1. This shell has energy level 2. And we got a bigger one that's even bigger, even further out. That's energy level 3, and so on. So an electron that happens to be here can be excited to a new orbit. Or it could be excited to the third orbit. It could be excited from here and then to there. It could be excited in a two-step excitation. Once it's up here, it can either relax straight back down, or maybe it's going to relax to the second level and then relax back down. Some of these relaxation patterns are responsible for things like phosphorescence. The fact that they absorb, you take a star, you put it on the ceiling in your room, you turn on the lights, it absorbs all this light, and then you turn off the lights and they glow for like half an hour or so afterwards. It's absorbed this energy and it drops down to a lower energy level where it doesn't release it all at once, but it slowly decays back down to the ground state when it stops glowing. So, but generally speaking, as the N increases, which is the principal energy level, the shell increases, as does the energy and the distance from the nucleus. And so does the number of subshells contained within. But generally you see here on this image, energy level 1, low energy. Energy level 2, a big jump. Then 3, a smaller jump. And then 4, a smaller jump, smaller jump, smaller jump. Essentially, when we looked at the photoelectric effect, we were calculating the energy it takes to make the electron go from 1 to infinity. But if this is getting smaller with each jump, infinity is not that far away. It's just how long does it take for the electron to completely escape the atom? How much energy does it take to push this all the way up to there and get it out? Now we'll probably, and we can probably go another slide or two. So, as I said, there are subshells. There are subshells in here. A subshell includes things like angular momentum term, L. With angular momentum term, essentially, is the orbital shape. How does these electrons move within a 3D structure? Where is the electron present? Depending on what's going to be the rho later, but depending on what shell we're in, depends on what shapes are possible. Now, this is something you may have to remember, learn, flashcards, something like this, but the shells are given various letter designations that have certain shapes. They come back to how the lines looked in the line spectrum, so don't really worry about. There's a reason why it's called S, P, D, and F, but we're not going to really worry about them. But just that the letters for the basic shapes, S is the simplest one, followed by P, followed by D, followed by F. We're not going to worry about F too much, but it's there. S is our simplest understanding of one. It is a single lobed sphere. It is simply a hollow sphere. The electron is somewhere on the surface of that sphere. Now, when the principal quantum number n is 1, we have 1s. There's only one orbital possible, and that's on the level 1 s shape. When we have level 2, we have two possibilities. We have the 2s, which is another sphere, but we also get the p. So we have the possibility of 2p orbitals. Now the p, if the s had a single lobe, the p has a double lobe. It looks like some sort of dumbbell or a bow tie or a figure 8. It is essentially two hollow Q-tips, essentially the ends of a Q-tip, where it reaches 0 at the dead center. And because of the nature of this shape, S was all dimensional, or essentially one dimensional, or 0 dimensional. It has no kind of designation on the X, Y, Z axis. When we get to the P, suddenly there's designation of, oh, it could be on the X axis. Oh, it could be on the Y axis, or it could be on the Z axis, because it's all 3-dimensional. So we have p orbitals, we have two lobes, like a figure 8. There's a px, py, pz. I'm going to go back to the doc cam just to kind of better show this. But that help us. So our nucleus, we have at first 1s. Then we have, so there's a 1s. Then we have a 2s bigger and around it. But in addition to the 2s, we also have our p's. There's one p. There's another p. And then we have a third p. That's our, well, say px, our py, and our pz. And then we could then have a 3s that's even further out, and a 3p. And we're going to build into the d as well. And so it keeps on building outwards with each step. And each orbital is contained within the previous. We'll finish with probably this slide. I mean, it will load. That's well, pardon me. Okay, so when we get to D and F, D orbitals have 4 lobes. So they look like a clover leaf, or in one situation, it looks like a wheel and an axle. But those have 2-dimensionality, like XY or XZ or YZ, Z squared. There are 5 different possibilities. And then F, which is the one we really, really want to look at, have all 3 dimensionalities at once, like XYZ or FX or XZ squared. They look like crazy flowers. And there's 7 different possibilities. But long story short, as we deal with the periodic table, these orbitals will become kind of match up with the location in the periodic table. Groups in group 1 and group 2 typically deal with electrons in the s orbital. Elements that deal with the p orbital, the 3p orbital, will be in the non-metal categories, the 3, the 4, the 5, the 6, the 7, the 8. Group 3 through 8, 3A through 8. Guys that have the 5 different D categories will be a transition metal. Those transition metals will be putting electrons into the D. And the Fs, are going to be the lanthanides and the actinides. The guys that the whole row of 14 elements at the bottom of the periodic table are dealing with these F orbitals. So we will not really deal with the lanthanides and actinides much. So we will not deal with the F orbitals very much. But that's where we'll stop. We will continue from there, looking more at these electrons, these orbitals, these energy levels that the electrons are in within the cloud. Please, quick reminder. Test is due next Wednesday. Be working on it. Be ready to turn it in on Wednesday. You can either email it to me, you can turn it in person. I really don't care how you get it to me. The important thing is that I get it. Make sure you used a separate shade of paper or typed it out. I really don't care. I'll manage to do it one way or the other. Just show your work. That's where I'll stop. Have a good day.